Have you ever really stopped to think about the device you're using right this second? I mean, it's basically a box of refined sand, metal, and plastic. And yet, it connects you to the entire world, runs unbelievably complex software, and seems to understand your every command. It feels like magic, doesn't it? Well, today we're going to pull back the curtain on this everyday magic.
So let's just dive right in with the big central question. How on earth does this inanimate object follow our instructions? How does it actually work?
To get to the bottom of that, we're going to build our understanding from the ground up, piece by piece. We'll start with what a computer even is, peek inside its brain, learn its language, check out its memory system, see how it thinks, and then zoom out to see how all this leads to the supercomputers that are shaping our world.
Okay, let's get into it. Before we can understand how a computer works, we need to agree on what it actually is. I know, it sounds basic, but its core identity is really important.
The absolute keyword here is programmable. Think about it. A simple calculator is built to do one thing, math. But a computer, you can give it a totally new set of instructions, a new program, and it can solve a completely different problem. That's the game changer right there.
So, if a computer's main job is to run all these different programs, what's the part that's actually doing all the heavy lifting? Let's take a look inside the engine room. Meet the central processing unit, the CPU. This thing is the absolute heart of the machine. You can think of it as the command center where all the important action happens. And it's really made of two crucial parts that work together. Okay, so this is where the raw number crunching goes down, the arithmetic logic unit, or ALU. This is the mathematician in the duo. It's doing all the adding, subtracting, the math. But it also handles logic, which is just as important. It answers questions like, is 64 greater than 65?
So if the ALU is the mathematician, the control unit is the director of the whole show. It doesn't do any of the math itself. Nope. Instead, it reads the program's instructions and just tells everyone else what to do. It tells the ALU what numbers to crunch and tells the memory where to get the data and where to put the answers. It's the ultimate orchestra conductor.
Right, so we've got a director and a mathematician in the CPU. But what language are they speaking? You might be shocked at how incredibly simple it is.
The entire, and I mean entire vocabulary of a computer starts right here, with a 0. You can think of it as off.
And this is the only other word it knows, a 1, which means on. Seriously, that's the whole thing. Now let that sink in for a second. Every single photo you've ever seen, every song you've listened to, every app on your phone. At the most fundamental level, it's all just a ridiculously long and complicated sequence of these ones and zeros.
Each one of these digits is called a bit, and inside your computer's CPU, there are literally billions of microscopic transistors that act like tiny little light switches. Each one can either be off, representing a 0, or on, representing a 1. That's the physical reality behind the computer's super simple language.
Okay, so the CPU is juggling billions of these bits all the time. But where does it keep them while it's in the middle of a task? It needs a workbench, a workspace. We just call it memory.
The main workspace is called Random Access Memory, or RAM. Think of it as the computer's short-term memory. It's incredibly fast and holds all the data for the programs you have open right now. The catch? It's volatile, which means when you turn the power off, poof, everything in it is gone.
But here's the thing. Memory isn't just one big bucket. It's a hierarchy, a pyramid. The fastest, most exclusive memory, called registers, is actually inside the CPU, but there's hardly any of it. Then you have cache, a little bit slower but still on the CPU chip. Then you have RAM on the motherboard, and way down at the bottom, your big, slow storage drive. The computer is constantly, cleverly moving data between these levels to give you the best of both worlds, speed and size.
All right, we've got the brain, we've got the language, and we've got the workspace. Now we can finally put all these pieces together and see how a computer actually follows a list of instructions, how it thinks.
I really love this analogy. A computer running a program is a lot like us reading a book. Most of the time, it just goes line by line, step by step. But sometimes, it gets an instruction to jump back and reread a chapter, or to skip ahead a few pages if a certain condition is met. This ability to loop and make decisions is what makes computers so incredibly powerful.
And this is what those instructions actually look like, way down at a low level. This is a language called assembly. Because the CPU can only do really simple things, we have to break down a big task, like say adding up all the numbers from 1 to 1,000 into these tiny little baby steps.
You can literally see the commands here: add, compare, and then that crucial command to loop back and do it all again.
So to run that code, the CPU does this simple four-step dance, over and over and over. It fetches an instruction, the control unit decodes it, the ALU executes it, and the result gets stored. Fetch, decode, execute, store. That's the heartbeat of the computer, and a modern CPU does this billions of times, every single second. It's just wild.
Okay, let's zoom all the way out. We've seen the fundamental pieces, a simple on-off switch, and a basic four-step cycle. How do we go from that to the mind-boggling power of modern computers?
Well, it's a story all about getting smaller. Those on-off switches started out as big, hot, unreliable vacuum tubes. Then came the much smaller, more reliable transistors. Then we figured out how to cram thousands of those onto a tiny integrated circuit, which led directly to the very first microprocessor back in 1971. The basic logic never changed, just the scale, and it changed dramatically.
Get this, that first microprocessor from '71 had about 2,300 transistors. The chip in the phone in your pocket right now, it has over 15 billion. That incredible density is why your smartphone has way more computing power than all of NASA had when they put a man on the moon. And today's supercomputers, they link together thousands of these modern chips to tackle problems we once thought were impossible, like forecasting weather across the globe or simulating new medicines.
So, from a simple on-off switch, literally made from sand, performing a simple four-step cycle, we've built machines that can simulate the entire universe. It's an absolutely astonishing journey of scale. And it leaves us with one last huge question to think about. If these simple rules can create this much complexity, what comes next? Are there any limits at all?